Welcome to my first lecture in complex analysis. First, we have to start by the basics, which is discussing the complex numbers. And before we can actually do that, let us discuss why we even care about complex numbers. Now, mathematically, it is interesting to think about the number square root of minus 1. Alright, because many things have been studied prior to the introduction of the complex numbers, the real numbers and rational and irrational and their properties and everything and all of that. And the reason why the complex numbers were also called imaginary is because at the time it was not quite clear what sort of real world application they could have, and they kind of only showed up in this mathematical form, which might be unrelated to what is going on in the real world, and it might not really have much sense to it, or at least at first thought. And that is why it's interesting to study this, because it was called imaginary, but just because we can't really understand it well at first, it does not mean that this is not real. It might be not part of the real numbers, but it is very much a real number in the physical sense. So this is what was defined as I. If this is the first time seeing this, you must know this, you must remember this. Okay, and why is this important to us? What sort of application does not only this I number have, but in general, right, the complex numbers? Why is complex numbers and why is this complex analysis important? Well, in physics, it has many applications. Now, it is used when describing traveling waves, and by extension, it is very important in quantum mechanics, and of course, many other in optics it's used, and other sort of fields where they use waves. It's also very important, for example, in the conformal field theories, which is somewhat more advanced, and it has many other applications. So it's extremely important that if you study physics and mathematics, you have to understand this, because it just pops up everywhere. It's actually crazy how much it pops up. Okay, so we just went quickly into the whys. Now let's dive into the hows. So before we begin, we must be clear about how we work with these I numbers. And for that, let us now take a look at the powers of I. So I squared, I cubed, that does not look like a cube, and I to the fourth power. So I, of course, is I, and I squared, well, what would this be? This is simply the square root of minus 1, which is I squared. So this is simply minus 1, okay? You have to know this by heart after this course. So you have to see an I squared and immediately think minus 1. That connection has to be made in your brain. Now, what is I cubed? I cubed is simply I squared times I. But we know that I squared is a minus 1, so this is simply minus 1 times I, which is simply minus I. And I to the fourth power, you can see it as I squared times I squared, which is minus 1 times minus 1, which is simply 1. Alright, so those are the fundamental properties that you must understand, not necessarily know by memory, except maybe I squared, because you can always determine the rest using I squared. And if you ever encounter something like I to the fifth, I to the sixth, I to the seventh, or anything like that, you can always go ahead and decompose it as I to the fourth, which you know is 1, times whatever is left. So like in this case I, in the case of I to the sixth, it's going to be I squared, and in the case for I to the seventh, it's going to be I cubed. Right, so we get these results. Well, and they are the same that we had before. So it's important to note that the powers of I are cyclic, so you get I to the first, second, third, and fourth power, and after that it's just repeating and repeating. Okay, so if you ever encounter I to some big power, you only have to know, okay, which is the closest power of 4, and after that you start counting. Okay, so that is the powers of I. Now let's dive into some of the actual complex numbers. So what do we mean when we say a complex number? Now, when we say that, we usually think of the letter Z, which is what we use to depict a complex number. And a complex number has two parts. it has what we call the real part, which is A, and the imaginary part, which we call B. And usually we write it as a sum of both parts, and the imaginary part has this I attached to it. So this is the general form to write a complex number. And you can also call this by introducing what we call the real part of Z, because as we said, the real part is the part that does not include the imaginary part. So you might as well just write, instead of A, Z, noting that this is of course A, and instead of B you write im of Z, which stands for imaginary. So B is the imaginary part of Z. Now I just wanted to write this because this notation actually is used quite a lot, so I just want you to know that it is there. Now, what else is important to know? There's also what we call the complex conjugate of Z, of a complex number, which is Z bar. And this is simply exactly the same that you had before, but this time you add a minus in front of what you have here. So if this was negative, now it's positive. If it was positive, now it is negative. So in general, it's simply minus IB. Okay, so this is the complex conjugate. So let me just write it down for you. Complex conjugate. Okay, and now with the basics out there, let's start working with some of the mathematical or arithmetic properties. So most of them actually work out basically the way that you would expect. So if you have any complex numbers, let's call them Z1, and this is just going to be 2 plus 3i, for example, and Z2, let's just call it maybe 3 plus 2i. And we want to add these together. So we want Z1 plus Z2. So in this case, the way in which we add this is that we sum the real part with the real part and the imaginary part with the imaginary part. But we do not mix each one of those. So you do not ever add what has an I with what does not have an I. You keep them separate. So 3 plus 3i is not 6i. You know, don't ever make that mistake. It's very important. So in this case, we have 2 plus 3, which are the real parts. So it's 5. And then we have 3 plus 2i, so we get 5i. Okay, so nothing really too surprising there. And of course, with subtraction, it would be the same thing. Now that we know how we operate the addition, let us now just discuss a quick thing. So notice that the form of our complex numbers is something real plus I times something that is some other real number that is of course with the I, right? So it is possible that you will come across something like, let's say 3 minus I plus 2i squared minus 4i cubed, for example. And in this situation, we have some higher powers of I. And of course, this could be anything. You could have higher powers of I. But the point is that if you encounter something that has powers of I that are not just I to the first power, so just I, then you have to simplify this first. Okay, you have to do that. When we work with complex numbers, we want them to be in the simplified form. Okay, so you cannot just leave it like this. And to do this, we use the properties of the powers of I. So this would be 3 minus I, that stays the same, but I squared we know is minus 1. So instead of plus 2i squared, we get minus 2. And then we have minus 4i cubed, but I cubed is minus I. So the minus turns into a plus, and we get plus 4i. So now we just add everything together, and we get 1 plus 3i. Okay, that was just a quick comment. So we have seen addition and subtraction. Now let's discuss multiplication. So once again, if we have any two complex numbers, so let's just say 2 plus 3i, and maybe this is going to be 1 minus 4i. And now we want to multiply both of them. So z1 times z2. What do we do here? Well, just plug in z1 and z2. So we get 2 plus 3i, 1 minus 4i. Okay, perfect. And from here, you just multiply normally. So we get 2 times 1, so we get 2. 2 times minus 4, so minus 8i. And then we have 3i times 1, so plus 3i. And finally, minus. And this is what can be tricky. I've corrected many exams on this topic. And this is where people, even at the college level, make mistakes. So this is minus 12i squared. And the I squared now is minus 1. So this minus sign in front will turn into a plus sign. And that is something that people forget, or maybe people just make a mistake and don't take the minus sign into consideration, or maybe they take another minus sign into consideration, because sometimes you have minus times minus and then another minus sign, so it can get somewhat confusing. So make sure to do the multiplication very carefully. It's not difficult, there's nothing new to it except for the fact that you are going to get this minus sign that can get you in trouble if you are not careful. Okay, so now we add everything together and we get 14 minus 5i. Alright, and we are once again in the standard form of a complex number. Now let's go into division. So let's now divide these two numbers. Now, what would this look like? We get 2 plus 3i divided by 1 minus 4i. Now, what is the problem here? The issue is that we have an I in the denominator. This I messes with the normal form that we have. If this was just a real number, we could just write these separately and then we would have something of this form, right? Real plus IB, right? A plus IB, that's what we're looking for. But here we don't have this. So we are going to use a trick. And that is to multiply by the complex conjugate of what is down here. Now what that means is that we multiply and divide. Of course, this must be the same because this is just multiplying by 1. These two can cancel and it's just 1, so we're not doing anything illegal. Everything is fine. And the idea of doing this is that, well, we're going to get something that is somewhat annoying upstairs, but now downstairs we now have a difference of the squares. So we get the first term squared minus the second term squared. But the second now has an I squared. So we get a second minus sign, which will cancel out the other one. So we get 1 plus 16. And now all of a sudden we don't have an I here anymore. That is why we did this. Okay, the reason we multiply by the complex conjugate is because we get this difference of the squares, which will square the I and get rid of it. But the cost to pay is that now upstairs is going to be somewhat less nice. So let's do the multiplication. So we get 2 times 1, which is just 2, plus 8i, plus 3i, and then we have 12i squared, so minus 12. So let's now add everything together and we get minus 10 plus 11i divided by 17. And just for completeness, we want to write this in our standard a plus ib form. So it's minus 10 divided by 17 plus 11i divided by 17. This is of course the same that we had here, but we're just emphasizing the structure that we want to have. Now, finally, I just want to make a quick remark and go back to the notation that I introduced about the real and imaginary parts. So remember, z we can write as not only a plus ib, but also as the real part of z plus I times the imaginary part of z. And similarly, we can now write the complex conjugate of z, z bar, as the real part of z minus I times the imaginary part of z. And now we can add these two together so that we can find an expression for the real and imaginary parts. So let's add them first. So 1 and 2, and we can add them first. And we get z plus, I'm going back and forth between saying z and z, I apologize for that. Z plus z bar, this is equal to 2 times the real part of z. And the imaginary parts cancel out. And now we can find that the real part of z is equal to z plus z bar divided by 2. Okay, so this is quite a useful thing to know. It does pop up from time to time. It isn't used all that often, but it is good to know that it exists, so that if you ever need it, you know how to find it. As you saw, it is not difficult at all. And we can do a similar thing for now the imaginary part. So if we subtract these two equations, now this minus will turn into a plus, and these two parts will cancel each other. So we get z minus z bar. This is going to be equal to 2i times the imaginary part of z. So we can now determine that the imaginary part of z is going to be z minus z bar divided by 2i. All right? So these two are quite important to know. At least know that they exist and be able to find this form if you ever need it. Now, we're going to see one last thing in this first lecture, and that is we want to now discuss the complex plane. Because now that we have complex number, it is very, very useful to find ways of representing these numbers. So we introduce the complex plane, which is going to be also a Cartesian plane, very similar to the one that you have undoubtedly seen before. And the y-axis is going to be the imaginary part of our points z, and the x-axis is going to be the real part of our points z. And how do we represent a point? Well, recall that any z is simply a plus ib, with a being the real part of z and b being the imaginary part of z. So we can now graph any point into this complex plane. We can, for example, have some point z here, which will have the coordinates a, comma, b. Okay, and now we can view it as a two-dimensional vector because we have always these two linearly independent parts in this number. It's basically this number z, but now it has two parts. It has this real and the imaginary part. That's why we now can sketch it in this two-dimensional representation. And now it's very interesting to find the distance of this number z to the origin. And this distance is calculated the same way we always calculate distances. So we can now just sketch each one of the sides of this triangle, and this vertical part is going to be the imaginary part, b, and this part here, this horizontal part, is going to be the real part of z, which is a. So now the distance here is what we call the modulus of z, or the absolute value of z. And we can find this using the Pythagorean theorem. So we know that this modulus squared is going to be a squared plus b squared. Okay, so this is very, very important. And of course you can from here see that the modulus of z itself is going to be the square root of a squared plus b squared. We do not take the possible minus sign into consideration because distances have to be positive definite. Okay, they have to be positive. It is not valid for it to have a minus sign in front. And now a final thing to note is what happens if we have the product z times z bar. So let's just use it in general. So let's use z equal a plus ib and z bar equals a minus ib. So let's just do this product. So we get a plus ib times a minus ib. And when we do this, well, this is once again just the difference of the squares. So we get this first one squared, which is a squared, minus the second one squared. But the second one squared is b squared, I squared. So we get another minus sign, which will cancel out the previous one. So we get plus b squared, which is exactly the same that we had here. So we can see that z times z bar is actually just the modulus of z squared. This is another very, very important property of the complex numbers that we will definitely be using quite often. All right, and just some few final remarks that you need to know about the absolute value or the modulus. So if you have the absolute value of some division, then you can write this as the absolute value of each one of them. right? If you are unsure, you can just go ahead and plug some values in and see that this works out, or maybe go for a more thorough proof, but this is also something that happens with the real numbers, so I hope this doesn't come as much of a surprise. And a similar thing will happen if we have, for example, the absolute value of z1 times z2. So we can just write this as z1 modulus z2 modulus. Okay, so those are the basic properties of the complex numbers. We will now start to use them in the next video, where we will discuss some sets of complex numbers in the complex plane. So I will see you in the next video. Thank you very much.